Okay, so lecture 15 in linear algebra. And I want to review a little bit of what I did this morning. So let V be a vector space. Let S be a finite subset of V, and not just the set consisting of the zero vector. And suppose we let W, which I sometimes write as S in brackets, be the vector subspace of V generated by S. That means W is the set of all linear combinations of vectors in S. So if S, for example, consisted of a finite set of vectors, what was the way that I wrote it down? W1 up to WK was the notation I think I had used. In that case, this set W is all linear combinations C sub I Wi, I going from 1 up to K, where the C sub i's are scalars. Real numbers, complex numbers, whatever the field of your vector space is. And we proved the following theorem already twice. So we have S is this finite set of vectors, and not just the zero vector. And W is the subspace that S generates. Let's say there are M vectors in S. Let V1 up to Vn be vectors in W. And the theorem says that if n is bigger than m, if you have a subspace generated by m vectors and you choose n vectors in the subspace at n greater than m, then the set of vectors or the sequence of vectors is linearly dependent. And a consequence of that was the following theorem. It says that I just want to try and state it the way I did this morning. Before I did that, I had proved another result, which said the following. Let S be the set of vectors, and it generates a vector space W. Then S contains a linearly independent subset that generates W. So here we have a set of vectors, and all the linear combinations of these vectors produce this subspace W. But these vectors might be linearly dependent. And the theorem says if they're linearly dependent, you can throw away some vectors and get a smaller set of these vectors, which still generates the same subspace, but is now linearly independent. So you have a subspace for which you have a generating set of linearly independent vectors. And such sets of vectors are very important in linear algebra. We say that a basis for a vector space V or a subspace of V is a set of vectors that has the following two properties. First set of vectors, I'll call it set B for basis. B generates W, and B is linearly independent. And an important problem in linear algebra is, given a subspace of a vector space, find a basis for the subspace. And there's a very important consequence of our previous theorem about the size, the number of vectors in a basis. And that's the following. Suppose we have two bases for the same subspace. So suppose B1 consists of m vectors, and B2 be a set consisting of n vectors. And suppose these are two bases for the subspace W, then in fact they have to have the same cardinality. The number of elements in B1 equals the number of elements in B2. Or in other words, M equals N. This, when you put absolute value signs around the set, this is the cardinality, which means number of elements in S. So the theorem, which I proved this morning, says any two bases for a vector space must have the same number of elements. And the proof is a consequence of a previous result. So we have B1 generates W, and B1 has M elements. B2 contained in W is linearly independent, and it has N elements. And we proved that if you have more than M elements in a space generated by M elements, then your set is dependent. So if you have a set of N elements that's linearly independent, the number of elements in the linearly independent set has to be less than or equal to M. But then you reverse the argument. B2 also generates W. B1 is contained in W and linearly independent. Cardinality of B2 is N, cardinality of B1 is M. If these vectors are linearly independent, then M is less than or equal to N. And if you have two numbers and each is less than or equal to the other, they have to be equal. So that is the proof. And this is really important. This is sometimes called the fundamental theorem of linear algebra. It certainly is one of the fundamental theorems. It says that, so we might state this as a corollary, but it's really just a restatement. Let V be a vector space or subspace generated by a finite set. There is a positive integer n such that every, this is the important thing, every basis for V has exactly n elements. And we call n the dimension of the vector space V. It's written din for dimension. Dimension of V equals n. And what we just proved is that the dimension of a vector space is well defined. Right? So for every vector space, there is a unique dimension. So, for example, so this is the fundamental example. Take the vector space Rn, which is all n-dimensional column vectors. And I've always said this is an n-dimensional vector space, so I have to prove that this is correct. That is, I have to find a basis for this vector space consisting of n vectors. And the simplest basis is, for example, we have what are sometimes called the unit vectors. So E1 is the vector with the 1 in the first coordinate and everything else 0. E2 is the vector with a 1 in the second coordinate and everything else 0. E3 is the vector with a 1 in the third coordinate and everything else 0. And so on. En is the vector with the 1 in the last coordinate and everything else 0. So here we have n vectors, and it's easy to check these are linearly independent. And if you take the vector x1, x2 down to xn, that's the same as the vector x1 with all zeros, plus 0, x2, and the rest all zeros, and so on, up to xn. And then I can factor out the x's. This is x1 times the vector 1, 0, 0, 0, and x2 times the vector 0, 1, and the rest zeros. And xn times the vector all zeros down to 1, which is x1 e1 plus x2 e2 plus xn en. So, yeah. So every vector is a linear combination of e1 up to en. So e1 up to en generates Rn. And if this linear combination is 0, if this is the 0 vector, all the x's are 0. So these vectors are linearly independent. And that is the proof. Any questions about this? These are fundamental concepts. I mean, we started off the course with very computational things with linear equations, and that just gives you a flavor of what underlies the theory of linear algebra. But from now on, everything we do has to do with the properties of abstract vector spaces, not just Rn. So I'm going to prove a few results about dimension, and then we'll introduce certain functions from one vector space to another. So this is in the new set of notes. This will be, I have a new set of notes that I'm going to post tonight, I think. Theorem 310. It says you have a vector space V and let S be a set of k vectors that is linearly independent. Let this be a linearly independent subspace of the vector space V. And let W be the subspace of V that is generated by S. So here you have your vector space V. Sitting in V, you have a set S, and it generates a certain subspace W. And it could be that W equals V, and it could be that it's not. So suppose W is not equal to V. That means it's a proper subspace. So there's some vector V that's in V minus W. That means everything in V that's not in W. So in this picture, this part that I'm shading in green is V minus W. Everything in V that's not in W. W is here. And everything in V not in W, that's the green. And I choose any vector in V, and I claim that the set S together with V, so that's the original k vectors in S, together with V, is a bigger linearly independent set. And the proof is by contradiction, because a set is either linearly independent or linearly dependent. So let's see. So suppose that we take scalars, x1, x2, xk, and x, that these be scalars such that this linear combination x1 w1 plus x2 w2 up to xk wk plus x times this new vector v equals the zero vector, equals 0. I want to show all the coordinates, all these coefficients, the x's are 0. Suppose not. Suppose x, this coordinate, suppose x is not 0. In that case, I can solve this equation for v. If x isn't 0, minus xv is x1 w1 up to xk wk. Just put this over to the other side of the equation. And because x is not 0, I can divide by it. And minus x over minus x is 1. So this is v. V is a linear combination of w1 up to wk. So v is a linear combination of W1 up to WK, which means V is in the subspace that W1 up to WK generates, which is W, and that's a contradiction. That's false. It's false because V was chosen not to be in W. So therefore, the coefficient of V, the X, must be 0. Right? So we have a linear combination of these K plus 1 vectors. If X is 0, I'm led to a contradiction. So X has to be 0, which means that all this has to be equal to 0, the rest of it. That is. If this X is 0, then X1, W1 up to XK, WK equals the 0 vector. But we know that the set S consisting of these K vectors is linearly independent. So if a linear combination of the W's is 0, all these X's have to be 0. Which means in this linear combination, if this linear combination is 0, every coefficient has to be 0, which means that this larger set, S together with the vector V, is linearly independent. That's what I wanted to prove. Now, let's see what else we can prove. So this in the notes is listed as lemma 3.1. And again, we have a vector space V and a subspace W. And so let W be a subspace of V, and the dimension of V is equal to n. So V has a basis with n vectors. Now, suppose we let W1 up to WK be a linearly independent subset of W. So sitting in here, we have K vectors that are linearly independent, but these K vectors are contained in V, and they're contained in W, and W is contained in V. So these K vectors are vectors in V, and V has dimension n. That is, V is generated by a set with n elements, so K is less than or equal to n. Because V is generated by a basis, a set, that contains n vectors. And our theorem said that if n vectors generate a set, and you have a subset of K linearly independent vectors, K is less than or equal to n. So You can't have arbitrarily large independent subsets of W. The largest any linearly independent set of vectors in W could be is K. And for that reason, you can choose a largest set of linearly independent vectors in K. So suppose we let S1 be a largest set of linearly independent vectors in W. And if S1 contains m vectors, m is certainly less than or equal to n, because it can't contain more vectors than n. Suppose we let W1 be the subspace of W generated by these m vectors. So sitting inside of W, we have the subspace W1. So here's our picture. We have a subspace W1. We have a linearly independent set of vectors inside of W, which generates a subspace W1. Suppose there were a vector in W which isn't in W1. So if there's a vector W star in W but not in W1, then by the lemma I proved a moment ago, if I take S1 together with W star, that's a bigger linearly independent set. And now this set has m plus 1 elements. But the largest subset of W that's linearly independent was S1 with m elements. There can't be a set of linearly independent vectors inside of W of size m plus 1. So in fact, this set S1 generates all of W. So it generates W, it's linearly independent, therefore it's a basis. And so that's what we did. So we just proved what we wanted to prove, that every subspace of V has a basis with at most n elements. Again, this is for most of you probably the first time that you've seen real proofs in mathematics. You don't really see proofs in calculus, and in any case, they're very computational. But this is what we do in mathematics. We prove results like this. And there are a lot more results that we can prove about dimension just using these kinds of abstract arguments. So again, this is in the notes. Theorem 311. You have some vector space V, and inside of V you have a vector space W1, and then you have a larger vector space, subspace W2. So here we have W1, and W1 is contained in W2, and they're both contained in V. So we have subspaces W1 contained in W2 contained in V. And suppose the dimension of W1 is K, and the dimension of W2 is L. And because W1 is contained in W2, we know that K is less than or equal to L. So the theorem says that if W1 up to WK is a basis for the small subspace W1, then there exist vectors W sub k plus 1, WK plus 2, up to W sub L in W2 such that the set of K plus L, K plus L minus K, so L vectors, so you take the union of these two sets, is a basis for W2. So this says if you have a basis for a subspace, you can always extend it to a basis for a larger subspace. And the proof uses the same idea we used a moment ago. So I have W1 up to WK, linearly independent vectors in W1. Suppose I can pick additional vectors in W2 that aren't in W1 to get a bigger linearly independent set. So let's say let W sub k plus 1, WK plus 2, up to W sub k plus r be a subset of W2 minus W1, not just any subset, a maximal subset. It means the largest possible subset of W2 and W1, such that W1 up to WK, K plus 1, these K plus R vectors form a linearly independent set. Now, the largest linearly independent set will have in most elements, so we know that K plus R is less than or equal to L, the number of elements in this set, because this has dimension L, so you cannot have more than L elements in W2 that are linearly independent. Let's call this set S prime, and let W2 be the subspace generated by S prime. So W2 prime. So W2 prime is contained in W2 because S prime is contained in W2. And then we can say the following: if W2 prime isn't all of W2, then there exists some vector V in W2 minus W2 prime, and S prime union this vector V would be linearly independent. But this contradicts the maximality of S prime. So that's a contradiction, because this set would have one more element than S prime, but S prime was the largest set of vectors in W2 that was linearly independent. So there can't be any vector in W2 that's not in W2 prime. So W2 prime equals W2, and S prime is a basis for W2. So that's the proof of that theorem. Again, I think it's impossible to understand what's going on just seeing this in a lecture. You really need to sit down with the notes and pencil and paper and spend a lot of time going through these proofs step by step, line by line, even word by word, to understand the reasoning involved. So I'll prove one more theorem about dimension. This is Theorem 312. Here we have a vector space, and in that vector space we have two subspaces, say W1 and W2. And they could overlap. That's certainly possible. So let W1 and W2 be subspaces of a vector space V that's finite dimensional. Say dimension of V is n, doesn't matter what the dimension is, so it's some finite number. So then the intersection W1 intersect W2. That's, if you look at this kind of Venn diagram, this red area, that's W1 intersect W2. That's everything which is in both W1 and W2. So this is a subspace. And each of these subspaces, every subspace has a dimension. Every subspace has a basis. We proved that a while ago. And what I'm going to write is W1 plus W2 is a subspace. So let me state the theorem, and then I'll just explain why each of these is a subspace. So the theorem says that for this big subspace, so W1 plus W2 is going to be some subspace that contains both W1 and W2. And the theorem says the dimension of the sum of W1 plus W2 is the dimension of W1 plus the dimension of W2 minus the dimension of the intersection of W1 and W2. So that's a very beautiful formula, and let me explain why that's true. First, I'll look at these two statements about subspaces. So let me just make sure we understand what the intersection and the sum mean. So again, here we have V. Here's the subspace W1. Here's the subspace W2. And this in here is W1 intersect W2. So what that means is W1 intersect W2 is all the vectors in V such that V is in W1 and V is in W2. It's all the vectors that are common to these two sets. So let's just check this is a subspace. Every subspace contains 0. So 0 is in W1 and 0 is in W2, which means 0 is in the intersection. So the first requirement for a subspace is that it contains the 0 vector. Second, it has to be closed under vector addition. So suppose we have two vectors V and V prime, and they're both in W1 intersect W2. So if V is in the intersection, V is in W1 and V is in W2. And if V prime is in the intersection, V prime is in W1 and v prime is also in W2. But if you look at this, v in W1 and v prime in W1, that means v plus v prime is in W1. And if you look at this, v in W2 and v prime in W2 means v plus v prime is in W2. So v plus v prime is in both of these subspaces. So v plus v prime is in the intersection. So the intersection is closed under vector addition. And the argument about scalar multiplication is similar. If v is in W1 intersect W2, then v is in W1 and v is in W2. If you take a scalar r, if v is in W1, it's a subspace, so CV is in W1. And v in W2 means CV is also in W2. And you put that together and you see that C times the vector v is in the intersection. So the intersection of two subspaces is closed under vector addition, scalar multiplication, contains the zero vector. So that's a subspace. That's a proof that the intersection is a subspace. And what does it mean to take the sum of two subspaces? How do you add subspaces? Well, the way you add subspaces is the following. It's all vectors of the form W1 plus W2, where W1 is any vector in W1 and W2 is any vector in W2. So you take any vector in the first subspace and any vector in the second subspace and add them, and that's what goes into the sum. So that's the sum of two spaces. Sum of two subspaces. And because these are both subspaces, 0 is in W1, 0 is in W2, so 0 plus 0 is in W1 plus W2. But of course, 0 plus 0 is 0. So the sum contains the zero vector. And suppose we have two vectors in here. Let's start with one. Suppose we take W equal W1 plus W2. We take W in the sum of these two subspaces. So you can write W as a vector in here and a vector in here. And then you have CW1 is in W1, because W1's in this, and this is a subspace. And CW2 is in W2 for the same reason, which means CW1 plus CW2 is in W1 plus W2. And this is just C times W1 plus W2, or C times W. So this is a proof that if you take a vector W in the sum of the two subspaces, for any scalar, C times W is in the sum. And why is the sum closed under vector addition? So suppose that W and W prime are in W1 plus W2. So that means that W is some W1 plus W2 for W1 in W1 and W2 in subspace W2. And similarly, W prime in this means W prime can also be written as W1 prime plus W2 prime for some vector W1 prime in W1 and W2 prime in W2. But W1 and W2 are subspaces. So if W1 and W1 prime are both in W1, that means W1 plus W1 prime is in W1. And if W2 contains both the vectors W2 and W prime, then W2 plus W2 prime is in W2. So if I take the sum of these vectors, W1 plus W1 prime plus W2 plus W2 prime, that's in W1 plus W2. But vector addition is commutative. This is the same as W1 plus W2 plus W1 prime plus W2 prime. And W1 plus W2 is W, and W1 prime plus W2 prime is W prime. So this is closed under vector addition. So the sum of two subspaces is a subspace, right? So this is, oops, what happened to it? Yeah, here it is. Yeah. So this is the theorem I want to prove. We have a vector space V, a subspace W1, subspace W2. The red is their intersection, and the green is the sum, W1 plus W2. And the theorem says the dimension of this very big subspace is the sum of the dimensions of W1 and W2, but we're double counting some vectors, so we have to subtract the dimension of the intersection. So that's the theorem I want to prove. So let me draw a picture again. Here's V, W1, W2, W1 intersect W2, and W1 plus W2. And the theorem says the dimension of W1 plus W2 is the dimension of W1 plus the dimension of W2 minus the dimension of the vector space in the middle, which is the intersection of the two. So proof. Suppose we let the dimension of the intersection be T0. The dimension of W1 be D1, and the dimension of W2 be D2. So to say the dimension of W1 intersect W2 is D0 means there's a basis for the intersection with exactly D0 vectors. So suppose we let W1, W2 up to WD sub naught be a basis for W1 intersect W2. Now, we proved if you have a subspace of a vector space and a basis for the subspace, you can extend it to a basis for the whole space. So here, where we had W1, sitting in it is W1 intersect W2. There exist vectors WD0 plus 1, WD0 plus 2. Maybe I'll index them 1 comma that, 1 comma this, up to W1, D1. So I have D1 minus D0 vectors such that these vectors plus these vectors this is a basis for W1 because W1 has dimension D1 and I have D1 vectors here. And similarly, there exist vectors W2 d naught plus 1 up to W2 d2 such that W1 up to W d naught, W2 d naught plus 1 up to W2 d2 is a basis for W2. So here I have D1 vectors. Here I have D2 vectors, but these sets have D naught vectors in common. Suppose I let B be the union of these two sets. So I have W1 up to W d naught, and then W1 d naught plus 1 up to W1 d1, and W2 d naught plus 1 up to W2 d2. So here I have d naught vectors. Here I have d1 minus d naught vectors. And here I have d2 minus d naught vectors. So I claim two things. B generates W1 plus W2, and B is linearly independent. If this is a linearly independent set, the vectors are distinct, and the cardinality of B will be d naught plus d1 minus d naught plus d2 minus d naught. One of the pairs of d naughts cancels. I get d1 plus d2 minus d naught, which is the dimension of W1 plus the dimension of W2 minus the dimension of W1 intersect W2. So if I can prove these two claims, I've proved the theorem. But now every vector in W1 plus W2 is the sum of a vector in W1 and a vector in W2. Every vector in W1 is a linear combination of these vectors. Every vector in W2 is a linear combination of these vectors. The sum is a linear combination of vectors in the set B. So that means B generates W1 plus W2. So the harder thing is to show that these vectors are linearly independent. So suppose some linear combination of these vectors is 0. So let sort of xi, yj, zk be scalars such that this linear combination x1 w1 plus x2 w2 up to x d naught w d naught plus y1 w1 d naught plus 1 up to y d1 minus d naught w1 d1 plus the sum plus these vectors. I'd have a z1 w2 d naught plus 1 up to z sub d2 w2 d2 is all equal to the 0 vector. So this is a vector in W1 intersect W2. This is a vector in W1 This is a vector in W2. So all we need to do is look at this carefully and rearrange it. We get the summation xi wi, I goes from 1 up to d naught, plus summation j goes from 1 up to d1 minus d naught, the yj w2j's equals minus summation k goes from 1 to d2 minus d naught, the zk w2k's. But this is a vector in W1, and this is a vector in W2. So this is a vector in W1 intersect W2. But a basis for W1 intersect W2 are just the Wi's. This vector has to be in W1 intersect W2, so all of these coefficients have to be 0. Which means this is 0, and these vectors are linearly independent, so all the xi's and all the xj's, all the yj's are 0. So the only linear combination of this big set of vectors that gives the 0 vector has all the coordinates equal to 0. So my set B is linearly independent. All right, so that really is a proof. It's maybe a little more complicated than anything I've done up to this point, so I think I'll start class lecture on Monday redoing the proof of this. But this is the kind of, if you like, abstract mathematical reasoning that we have to learn how to do now. So, any questions about any of this? I mean, I expect it's hard, but that's just the nature of the subject.
Yeah, because since this is all very abstract, I was wondering, like in exam 2, like if we will have to mainly be doing this kind of proof, right?
Yes. That's what one of the main things to learn in this course is how to give proofs of theorems in mathematics, and theorems tend to be abstract. Otherwise, it's just like, the beginning stuff. So this is the skill or technique that you have to learn.
Oh, it's gonna be tough, but I'll try.
Sure. Okay. That's all you can do. Okay, everyone. Study hard. Enjoy the weekend. Be back on Monday. Bye.
All right, bye. Thank you, Professor.